Hello everyone, welcome to my YouTube channel Chemistry Lover. Today in this video I have shown you hydrogenation of alkene using Wilkinson catalyst. That means from alkene we can obtain alkane using hydrogenation by using conventional method like nickel in presence of hydrogen or platinum or palladium metal in presence of hydrogen. But instead of using this, we can also use several catalysis like Wilkinson catalyst. You can see here, this is the chemical formula for Wilkinson catalyst, where we can easily obtain an alkane from the unsaturated compound or alkene in presence of hydrogen. So let us show the catalytic cycle. So first of all, this is the possible structure of Wilkinson catalyst. Since it is a square planar, so I have drawn the complex in this way. Now at the first step, oxidative addition of hydrogen take place on it, and since oxidative addition here take place in the cis manner, so here two hydrogen present in the cis form and coordinated to the metal center rhodium. So according to this, the other four ligands changing their position accordingly. You can see these two triphenyl phosphine are in transposition, and the chloride present here initially changed to this site because here two hydrogen are present, and the number of electron count should be also considered. First of all, it is a 16 electron system, square planar complex. I have already told you at the beginning. So due to oxidative addition of hydrogen, the number of electron also increases from 16 to 18, that is square planar to octahedral. Now at the second step, removal of triphenyl phosphine take place. Since triphenyl phosphine is a bulky ligand, so due to severe steady crowding, one triphenyl phosphine easily removed from the complex in order to increase the stability, and this step is very important for the overall process, right? So at the second step, removal of triphenyl phosphine take place. Here you can see the triphenyl phosphine I have removed from this side. You can also remove this triphenyl phosphine or this, doesn't matter, the overall product should be same. And I have removed the triphenyl phosphine from this side here, and the number of electron also decreases from 18 to again it get back to 16. And at the next step, the alkene coordination take place here. Coordination, the vacant side where the triphenyl phosphine is removed, at that side the triphenyl phosphine removed, and the vacant site created. This vacant site is again fulfilled by the alkene, which is coordinated to the metal center. Here you can see this is the third step. So here you can see the alkene coordinated with the metal center, and exactly at this site, first of all, a triphenyl phosphine present, but this triphenyl phosphine is absent now because I have removed it from the complex, and now the alkene present with the metal center at the site. And here migratory insertion take place because here two hydrogen present in this case, so between two, one of them undergo migratory insertion and coordinated to the unsaturated carbon of the alkene and form this type of alkyl group. Here you can notice that between these two carbon, one is less statically crowded but the other is more statically crowded. So in generally the addition of hydrogen should take place at this side, right, because it is less statically hindered. But here a more bulky triphenyl phosphine already present, so this addition could not be favorable at all. But this addition could be favorable because the chloride is less bulkier than triphenyl phosphine, though the carbon is more substituted. But here the addition of hydrogen take place and it is favorable due to less steady hindered chloride present nearby, unlike this. Okay, so here this type of product obtained. Again the number of electron count you should consider the number of electron count for all the possible complex, right, at every step. First of all 16, then 18, then 16, then 18, again it get back to 16, because one hydrogen undergo migratory insertion, that's why the number of electron count changes again. And here, in order to regenerate the catalyst in the initial form, we should eliminate these two groups, the hydrogen and the alkyl group. So these two groups eliminated from the complex, and the residual complex get back to the original mother form, and this is the overall catalytic cycle. So here are several important points also I should see. Here you can see. So first of all, here one important point is that the ethylene does not take part in such the catalytic cycle, rather it will directly replace the triphenyl phosphine group. The ethylene cannot take part in this case, because the catalytic cycle which I have shown you is only applicable for such unsymmetrical alkene, propene or pentene, right? Ethylene, since a symmetrical alkene, it readily replaces the one triphenyl phosphine group, and here that's why this such type of catalytic cycle not take place. And the second step, the removal of triphenyl phosphine from the complex is very important here, which I have already told you. And the third, the alkene must be unsymmetrical in this case, and at the end here these two complexes cannot show such type of catalytic activity, because here for both of them the removal of PPh₃ or PET3 does not take place, and since the second step is not favorable for them, hence the such type of catalytic activity is not possible. So up to this, if you have any doubt regarding this topic, then please ask me through the comment section below, and I will definitely sort out your queries. Thank you.